Well, we'll start out this chapter by just doing a real quick summary of everything that you've already read so far about gas laws. I realize that you've already done a couple of experiments that have probably done a pretty good job of illustrating a couple of the laws to you. I just want to make sure that all of this is really sinking in and try to give you a couple of illustrations so that you will be able to hopefully really visualize what these gas laws really mean. He starts out, the author of your textbook starts out by talking about pressure. And he says pressure is really force per unit area. And the best way I can explain that to you is to try to pretend that maybe your mom and your dad are going out on a date together and they're all dressed up because they're going to go to a really, really nice restaurant. You are running around barefooted, and so as mom and dad walk by, maybe you happen to get right into their path and they step on your foot. Now, mom, because she's dressed up, is wearing a shoe that looks like this, that has a really pointy heel on it. Now, what would you rather happen? Would you rather mom step on your foot with this pointy heel, or would you rather dad step on your foot, even though dad's probably a lot bigger and a lot heavier, but he's wearing shoes that look more like this, where they're nice and flat on the bottom? So what would be your preference? Well, I know my preference would be I'd rather have a nice flat shoe step on my bare foot than something with a really spiky heel. And the reason for that is because there's not a lot of area at the bottom of this spiky heel. It's a really, really small area. And so there's a lot of weight that comes down right on that spike, on that point. And so what happens then is that there's a whole lot more pressure on your foot because there's not very much area that's where that pressure is being applied. So that's the whole idea behind pressure, the amount of force per unit area. The more you can spread that force out, the less pressure that you're going to feel. So that's the concept behind pressure. Pressure is normally measured with a barometer, and I noticed when I read this that he said something that might have caused you to question what exactly he was talking about. The author talked about how when you make a barometer, you take a tube that has no air in it and you invert it. Well, how do you get a tube with no air in it? How does that happen? Well, generally when they make a barometer, what they'll do is they'll take a tube that's closed on one end and they'll fill it all the way up to the top with mercury. And then if they take that tube and they invert it and put the open end down in a bowl or a pan full of mercury, then what will happen is that the mercury will start to run out until pressure is equalized between the amount of pressure that's in the tube and the amount of pressure that's in the bowl. And so when the mercury runs out, then what's in the top is a vacuum and there is no air in there. So I just didn't want you to think that there was some magical way to get air out of a tube. The only way to get air out of a tube is to do like I said, you're going to fill it completely up and then invert it into a pool and then let it run out, which means there'd be no air in it, or you'd have to pump it out with a vacuum pump of some sort. Okay, it's really key in this chapter that you understand the concept of proportional, and specifically inversely or directly proportional. Okay, so there are two specific terms, and I'm assuming that you've probably covered them at some point in your math classes. If you have not, this is something that you want to try to grab a hold of. Proportional just means that you've got two factors and they're both changing. If they are directly proportional, as one goes up, the other is going to go up. Or if one goes down, the other one's going to go down. So they both change in the same direction at the same time. If something is inversely proportional, as one factor goes up, the other factor is going to go down. Okay, I can explain this pretty easily, generally for most students, with the amount of studying they do and the type of scores they get on a test. The more you study, the better the grades you're going to get, in generally. So, okay, so your grades and the amount of study you put in are directly proportional to each other. So as one goes up, the other goes up. Okay, you could think about that with how much you eat. The more you eat, the more your weight goes up. Okay, so those things are directly proportional. If you talk about exercise, if I think about it irrespective of how much I eat, the more I exercise, the more my weight drops, okay? So exercise more, weight goes down. So those would be inversely proportional because they're going opposite directions at the same time, okay? So now there are 3 specific relationships that we can talk about with gas laws. And there are 3 factors that we talk about: pressure, volume, and temperature. And when we speak of these relationships, we're going to hold one of those factors constant while we discuss the other 2. Now, in the real world, a lot of times all 3 of the factors change at once, but it's helpful to understand what's going on if we will hold one constant and just talk about the other 2. So the first law that you've already read about in your book is Boyle's law, and it says that if the temperature is constant, then if the volume goes down, the pressure is going to go up. So they are inversely proportional. A lot of times I like to think of gas laws in relationship to what it looks like with children on a playground. So gas molecules are moving around all the time, and if you've ever seen a playground full of kids, they're moving around all the time too. So the amount that the kids are running would be similar to the temperature of the gas molecules. The volume would be how big you have the fence around the playground. And the pressure would be how often the kids run into each other, because if you've seen a bunch of kids running around, that's going to happen. They're going to plow into each other. So in this particular scenario, if the kids are all running around at the same rate, and you shrink the playground and you make it smaller, and the kids are still running around just as fast, they're going to run into each other more often. And so that's what happens with your gas molecules as well. If the temperature is constant, so the temperature tells you how quickly the molecules are moving, if you shrink the amount of space that they have to move, the likelihood that they're going to hit the walls of the container or they're going to hit each other is going to drastically increase, okay? Charles' law says if you have constant pressure, if temperature goes up, volume will also go up because these are going to be directly proportional to each other. So let's assume, again, you've got the same kids on the playground. We don't want an increase in accidents, so we don't want them running into each other any more often than they already are, because we don't want the kids to get hurt anymore. So in this situation, let's say that I make the volume of the playground bigger, and so therefore the kids would be able to run around faster and more, and they wouldn't get hurt anymore. Now, if you think about it the other way, if the playground size of the playground shrinks, then the kids are going to have to slow down and not run as fast, or maybe you're going to even tell them they have to walk so they're not running into each other as often, okay? So just like with gases, if you don't want them banging into the sides of the container any more often, and you raise the temperature, you're going to also have to give them more space to move around in, okay? So the third relationship, he didn't really talk about this in your book, but the third relationship is still very much there. In Boyle's law, we've held temperature constant. In Charles's law, we've held pressure constant. And in Gay-Lussac's law, we hold volume constant. So if the volume is constant, if temperature goes up, pressure is going to go up. So they're going to be directly proportional. Again, if I think about my kids on the playground, normally I'm not going to be changing the volume of my playground any. It's going to remain the same size. If the kids start running around faster, they're going to run into each other more often. And so there would be more injuries. So similarly with a gas, if you have a, for example, like an aerosol can, like a spray paint can, and that volume is going to be constant because it's a very stiff-sided can. If you raise the temperature on it, the gas molecules start moving around faster and faster and faster, and at some point the pressure really goes up and your can could actually explode because your pressure gets too high. That's why you're never supposed to throw an aerosol can into a fire, because the pressure will rise so much that it will explode. Now, I mentioned this in your daily lesson plans. I do not expect you to be able to keep straight the difference between Boyle's law, Charles' law, and Gay-Lussac's law. I don't care that you know the name of the scientist that goes with each particular law. What I do want you to be very much aware of, though, is what happens if the pressure's constant and I raise the temperature, what happens to the volume? What happens there? So think about that down on a molecular level. Think about, okay, if temperature goes up, they're moving faster, they're going to be more likely to run into each other. So it's the relationships that I want you to understand and to know, not necessarily the name of each individual law. A lot of times, if you will think back to the lab experiments that you've already done, you will probably be able to keep these relationships straight when you think about the balloons that you used in these first two experiments. And with this one, you can remember the aerosol can example that I just gave you. One other topic that he mentions in the chapter is extrapolation. And so again, sometimes if you read something like this in the book, it's sometimes kind of hard to figure out exactly what he means. So I have a graph up here on the board, and I'll try to show you exactly what he's talking about. So in my graph here, I have volume on the y-axis, and I've got temperature in degrees Celsius on the x-axis. And so if you've run two different kinds of experiments, what you find with a gas is that the higher the temperature, the higher the volume. And so remember, we talked about that already with Charles's law. If you make the temperature go up, but you want the pressure to stay the same, then the volume's got to expand so that they've got more room to move. The lower the temperature, they don't require as much volume in order to keep the same pressure. Okay, so if I was testing a gas and I got these 4 data points as I was measuring the temperature and the volume necessary to occupy them, I could connect these 4 data points together and make this line. These 3 points here came from testing a different gas in maybe a slightly different container, and so the volume may have been a little bit different. And so these 3 points also connected together. Now when I extrapolate something, what that means is I take this line, and even though I don't have any more data points down here to connect it, I'm going to say, okay, if I would lay my ruler on this line and I'd go ahead and extend it back, where would it end up? So I would take that line and I would extend it back. And if I take this line and I extend it back, where does it end up? And so in your book, where he has much straighter lines than I just have been able to reconstruct here, what you see is that the volume and temperature coincide, or they intersect at a negative 273.15 degrees Celsius, and that's considered the temperature at which, well, actually you can't reach it, because at that point you would require 0 amount of volume, which is impossible, because if you have molecules, they have to take up space. That's one of the characteristics of matter. If matter is present, it has mass and it takes up space. But the idea of extrapolation and extending this backwards to this particular point is one that is going to be used as we talk about absolute temperature scales and the Kelvin scale, and the combined gas law, and why we have to do this. So in this video here, my main goal was just so that you understood the purpose of extrapolation. There's nothing wrong with extrapolation. And extending that data line backwards, as long as you don't get real crazy with it. If your data stretches over a big enough space and you're just extrapolating back a short distance in comparison to the amount of data you have, you can assume that more than likely what you're going to see when you do that extrapolation is going to be accurate. If you try to extend it back really, really, really far, at some point those extremes will no longer be accurate. So one of the rules for extrapolation is, however big this is, the amount of area that you extrapolate it back has to be small in comparison to the amount that you're extrapolating. Okay, I know that that was kind of a big smattering of information all at once, but I also know that you've already read most of that. You've done a couple of experiments already. So I just wanted to kind of bring it together and sum it up for you, give you some other explanations to hopefully help you cement those ideas in your mind.